Hey guys, welcome to today's video, which is about lattice enthalpy. Lattice enthalpy or lattice energy is simply the energy associated with completely separating 1 mole of ionic compound into its ions. So for example, for sodium chloride, if you had a mole of this substance and you wanted to break all the ionic bonds so that you had a mole of sodium cations and a mole of chloride anions, that would require that you put in 788 kilojoules for the mole. Remember, energy always has to go in when we are pulling apart or overcoming forces of attraction. Now remember that sodium chloride as an ionic compound does not exist as individual sodium chloride molecules. Ionic compounds don't do that. Instead, this sodium cation is attracted to a chloride anion, but that chloride anion is then attracted to another sodium, which is attracted to another chloride, and on and on and on until all the available sodiums and chlorides have been gathered up into this crystal. Ionic compounds always exist as solid crystals, at least at room temperature. So again, if you had a mole of this ionic compound, you would have to put in 788 kilojoules to disrupt all of those bonds and create individual cations and anions. So we're going to look at the specific amount of energy that is required to do that for a number of different ionic compounds. So let's take a look at a very abbreviated periodic table here and remind ourselves what we said in an earlier unit about size of cations and anions. First of all, we said that cations are always smaller than the atoms they come from. And furthermore, we said that just like the metal atoms that trend larger as you go down a group, the same thing is true for their cations. So cations will get larger as you go down a group, and cations will get smaller as you go across a period. Let's remind ourselves what we said about the anions. Anions are actually larger than the non-metal atoms they came from. And just like the non-metal atoms trend smaller as you go across a period, so do the anions. Anions get smaller as you go across a period, and anions get larger as you go down a group. So this would be the relative sizes of these anions and the relative sizes of these cations. Okay, so now one thing that you are expected to be able to do is to predict, not the exact numbers, but predict the relative lattice enthalpies if you're comparing two ionic compounds. For instance, here's an ionic compound, lithium fluoride, and here's another one, potassium bromide. So can you predict whether the lattice enthalpy, the energy needed to break up a mole of these ionic bonds, is that greater than the lattice enthalpy needed to break up a mole of potassium bromides? Is this lattice enthalpy greater, or is this lattice enthalpy greater? And it turns out, if you're asked to make that prediction, we're going to use Coulomb's law, our friend Coulomb's law. Now, we've been using Coulomb's law thus far to talk about the force of attraction between protons and electrons. Coulomb's law is equally valid to talk about the force of attraction between positive cations and negative anions. So Coulomb's law tells us that that force of attraction that we are trying to overcome with lattice enthalpy, that force of attraction gets stronger when charge is larger. In lithium fluoride, I have +1, -1. In potassium bromide, I have +1, -1. Okay. So no difference in the charges there. So let's ignore that piece of Coulomb's law and recognize force of attraction also gets weaker when the distance is longer. Now, the distance I'm talking about here is the internuclear distance. So think about the nucleus of potassium and the nucleus of bromide, and that internuclear distance is that long, compared to the internuclear distance between the lithium cation and the fluoride anion. Clearly, the distance is longer for potassium bromide, and when distance is longer, the force of attraction gets weaker. So Coulomb's law would help me predict that the force of attraction here should be stronger and therefore require more lattice enthalpy. And let's look here. This is in your book on 293. Sure enough, the lattice enthalpy for lithium fluoride is 1030, and the lattice enthalpy for potassium bromide is less, 671. Okay, let's do another comparison. Let's stick with lithium fluoride, and let's compare it to calcium oxide. So again, we want to try to predict which of these two ionic compounds requires the greater lattice enthalpy. Which one of those two is held together with a stronger force of attraction? Coulomb's law tells us that that force of attraction gets stronger when charge is larger. 1 + 1 - or 2 + 2 - Okay, so this compound has the larger charges, and so force of attraction should be stronger for calcium oxide. Now, you might also notice, well, but that's true, but also it has a little bit longer internuclear distance. Well, I'm going to tell you, as you use Coulomb's law to predict lattice enthalpies, this one is going to be more significant. If you have one compound with larger charges, that's going to win. Okay, that's automatically going to have the stronger force of attraction. Don't consider the internuclear distance piece unless the compounds that you're comparing have the same charges. Charge trumps distance as we consider Coulomb's attraction for lattice enthalpy. So looking again at page 293, sure enough, calcium oxide with this very large lattice enthalpy must have the stronger force of attraction than does lithium fluoride. Okay guys, I hope that was helpful.